Okay, so I don't know if you received my final email when I sent you on a Schoolsoft. We lost the video from the previous session. I don't know how many of you were absent. So I made another video. It's a little bit more complete than what we did in the lesson. So I uploaded it on YouTube and I send you the link. So I will consider that you have already seen that video. Okay, so because there are some new parts that I added to the video, even for the people who were in the lesson. Okay. Of course, if you have already been in the lesson, that's quite okay for this session. But if you were not in the lesson, neither you didn't study that one, it might be a little bit problematic for you. So I want to continue the lesson. I want to start from exactly again the permutations with repetition. Okay. So let us open the problem today. Example. So this is more or less a repetition from last time, but I will add more problems to it and see that how much we can go. So permutations with repetition. Okay, so we talked about permutations. So I told you that I give you a number of objects, assuming that they are distinct. Then I ask you to arrange them in a row, for example, so that the order matters. Yes. In that case, we learned how we can calculate the total number of permutations. But now, we of course talked about this, but let me again assume that I haven't talked about this and I start it again from scratch. Okay, so let me start with an example. So how many permutations of the letters A and B are there? Of course, this is a very simple problem. You can write down all of them. So let us just do it once. I have two A's and one B. I want to write all possible permutation of these three letters. Of course, with my handwriting, it would be hard to write identical A's, but I'm assuming that these A's are identical. So if they are interchanged, I cannot recognize the difference. So this is very clear. So what I can do, I can write A, and B. Then I can write A, B, and A. Then finally, I can write B, A, and A. Yes? This is the number of ways that I can arrange these three letters, two of them A, one of them B. And if you count the number of them, it is clear that this is 3. But I want to find a way that we can systematically count them. Okay, so let me tell you what is the systematic way of counting if we have some objects repeated in my list. And I am still want to use all of them in a row. So do you remember the strategy that we talked about a little bit last time is to momentarily assume that these A's are distinct. Yes, so instead of having two identical letters of A, let me put indices for them. I will call one of them, so I would assume that momentarily that I have A1, A2, and B. Okay, then my strategy is this. Try to write one of these permutations, for example, A1, let me start from here, A1, and then A2 and B. Okay, so if you remove the indices, it becomes AAB, which is this one. But now the strategy is to interchange the places. You are allowed only to interchange A's among themselves, not with B. Okay, this is my strategy. So what happens? I can interchange these two, so it becomes A2, A1, and B. Okay, There is no other options. But let me go to the other one, so I can have it A1, B, A2. This, if I remove the indices, it will give me this one. So let me interchange again A's among themselves. I don't care about B, I just interchange A's among themselves. So what happens here? It becomes A2, B, and A1. And if I ask you what is the next one, again, I can write B, A1, A2. If I remove the indices, it becomes this one, but I can also interchange these two among themselves. Okay? So you see that the items that I am interested in are only these three items. So it means that this item corresponds only to one single item that I want to count. Both of them, if I remove the indices, both of them represents exactly one item. Yes? And the same thing here. If I remove the indices, this gives me 1, A, B, A. It doesn't matter, this one and that one are the same. And the same thing here. This becomes B, A, A. Okay, so hopefully you have a strategy here. So you see that the number of items that are missing for me would be the number of columns. So that is the question mark, yes? Because the numbers that I am interested in are not all the items that you see here. From each column, there is one representative, and that is coming when I remove the indices. When I remove the indices, there is no difference between this one and this one. There is no difference between this and that. There is no difference between this and that. But still, even if I remove the indices, there are differences between these items and these items. If I remove these indices, they are AAB, but these become ABA. People can recognize the difference between them. So every item here will reduce to one single item if the indices are removed. But the items that are here and here and here are totally different. So I hope that you agree with me. The number of items that I want to count is the number of columns. Yes. So the number of columns is the answer to this problem. But now if you look at all possible situations, if you look at all the columns simultaneously, and if I ask you how many items you see in total, the total number of items, what is the total number of items? If I consider the indices, then I will have three distinct objects and three distinct positions. So the total number of arrangements, according to the theorem in the previous lesson, is how many? The number of total items is 3 factorial. Yes? And the depth of each one of these columns is 2, or better to say 2 factorial. There are two ways that I can interchange two A's with each other. Either you can write 2, or let me just use the theorem 2 factorial. And then it becomes clear. If I ask you how many total items you see here, you can calculate the total number of ways in two different ways. But because you are calculating the same thing, namely the total number of items, these two should match. On the one hand, total number of items is 3 factorial. On the other hand, total number of items is equal to the width times the height. Yes? The width is not clear, the question mark, multiplied by 2 factorial. What I wanted you to understand, I want you to understand these ways of countings, but because I am counting the same thing, they have to match. Yes? So this means that question mark multiplied by 2 factorial should be equal to 3 factorial. And I am looking for the question mark. So the question mark is 3 factorial divided by 2 factorials. Is that clear? So then hopefully you understand what's going on. Let us make the problem a little bit more interesting. So how many permutations are there I can construct using the letters in the word, for example, pepper? Yes. So example, By the way, these ways of talking in combinatorics is very common. So let me write it in this way. How many words can one construct so let me be more precise. So pepper, how many are there? So pepper, 1, 2, 3, 4, 5, 6. So how many 6-letter words can one construct using the letters in the word pepper? Okay. So please remember this way of asking questions. When I say how many 6-letter words, it means, and then you count the letters here is 6, it means that I want you to use all of them. Okay. So, and then here, of course, you might write a word that you cannot even pronounce, yes? So people cannot probably pronounce this, yes? But here you don't need to be worried about these things. So my point is not write a word which is pronounceable or write a word that is meaningful, okay? So when I say a word, you can just even write nonsense here, so no worries. And now you don't need to be worried about if it is possible to pronounce it in the first place. So these are these are very common in combinatorics because it takes a long time every time I want to explain these things. So here I have a word pepper, and I want to see that how many 6-letter words I can construct using the letters in pepper. Okay. Uh, So if I tell you what about table, if I ask you the same question for the word table, the answer is simple, yes? Because none of them is repeated. Of course, 1, 2, 3, 4, 5. This is 5. Okay, so I don't remember a 6-word letter again. But if I ask you how many 5-letter words you can construct using this, the answer is simple, 5 factorial, because none of the objects is repeated. But here the objects are repeated. Let me again use this strategy to understand it better, but then later you will actually use the formula if you want to. So what is the strategy? The strategy is, for example, let us consider the word pepper here, exactly in this combination. But let me just introduce indices for p's. I have 3 p's, so let me write p1, p2, and p3. And let me use indices for e's as well, so 1 and 2. I don't need any indices for r because that's just unique. Okay? Now the strategy is this. My strategy is to start permuting p's among themselves, so you are not allowed to change the locations. So if this is the first location, if this is the second location, third location, fourth, fifth, and sixth. Okay? I want you to start rearranging these letters, but this is the rule. You are only allowed to use position 1, 3, and 4 for p's. You are only allowed to use positions 2 and 5 for e's, and you have only one position for r, and that is the 6th position. If you stick to this rule of game, then you can write something here below that. For example, one possibility is to write p2 here. I don't know, let us keep E1 here. I can write P3 here. I can write P2 here. I can write E2 here, and I can write R. So I am following the rule. You see, I respected the rule that these are positions for P's, these are positions for E's. And you see that I have respected the rule. But from your perspective, this is different from that. People can distinguish the difference between this word and that word if the indices are there. But if I remove the indices, what will happen? This word and that word are exactly identical. Yes? Oh, thank you. Thank you. Thank you very much. This is P1. Thank you. Okay, and then is there another possibility here? I want to just do some of them. For example, let us keep P2 here. Let me interchange P1, so P2 here, P1 and P3 here, and let me write E2 here, E1 here, or there. So you see that still I am respecting the rule of the game. Yes, P's are in these positions, E's are still in these positions, R is still in that position. But again, if you remove these indices, these three words are not three different items. They are not three different words. They are actually exactly the same word. But I'm not patient to write them all. I want you to tell me, if I want to respect this rule, what would be the depth of this column if I start writing all of them? Without writing them, you are at the position that you can calculate this item, this depth immediately. So what would be the depth here? Yes? Exactly. Because if I want to stick to the rule of the game, I have actually three tasks. Put R in position number 6. There is one possibility for that. Just put it there and just real it. But I have two E's and I have two distinct positions. The second stage of my task is to locate E's. In how many ways I can do that? I can do it in 2 factorial ways. Yes? And then after this is accomplished, I go to the third stage. The third stage is that I want to see in how many ways I can locate 3 P's. They are distinct objects in 3 distinct locations. So that's 3 factorial. So according to the product rule, I hope that everyone agrees that the depth of this one is 2 factorial times 3 factorial. I intentionally write it in this way. I could written 12, but I intentionally write it because I want to find the pattern. Okay, but now if for this problem, for in this way, I have 12 items, but when it comes to my original problem, how many items I have counted so far? Only one, and that is the word pepper itself in this order. Okay, now let us go to the next one and then try to write a word which is even different from that word. For example, I put these 3 P's here. P, P, and then R, E, P, and E. Okay? So this is different from that word. Even if I put indices 1, 2, 3, and then 1, 2, but the rule of the game is here. This is the first position, the second position, the third position, fourth, fifth, and sixth position. Now the rule is that you are only allowed to give number 1 and number 2 and number 5 to P's, and number 4 and 6 to E's, and number 3 to R. Okay? This is the rule of the game now. So in how many ways I can arrange them? For example, one other possibility of arrangement is to put P3 here, P2 here, P1 here, and R here, E2 here, E1 here. Do you agree? This is one possibility. And again, I don't want to continue writing them down, but again, how many possibilities are there for this column? Exactly the same thing. Agree? But as far as my original problem is concerned, how many items I have counted so far? Only 2. One of them is this one if you remove the indices. One of them is this one if you remove the indices. And assume that you continue this strategy. You continue this strategy, and then I don't know, you have something at the end. So if I ask you what is the answer to this question, you would probably tell me that the number of columns is the answer to this problem. Is that understandable for everyone? So I have to count the number of columns. So the number of columns is the question mark that I want to answer for this problem. Okay, I want to count the total number of items. It is boring to write all of them, but assume that someone has already finished that, and it is possible because there are finitely many. I want to count the number of items after everything is finalized in 2 different ways, but because I am counting the same thing in 2 different ways, they have to match. Okay, so tell me, how many, so let me write the total number of items. I want to count it in 2 different ways. So the total number of items the total number in two different ways. Okay, let us just do it very simply. How many columns I have? Question mark columns. What is the depth of each column? 2 factorial, 3 factorial. So it is clear that if I multiply this question mark by 2 factorial, 3 factorial, it definitely gives me the total number of items. Yes? But on the other hand, that is I want you to understand. What is on the other hand? How can I count a total number with a different strategy? Yes, how should I do that? Yes?
We use the strategy to count if all the objects are
Distinct, yes, because if I am assuming that all the objects are distinct, I have given them indices. So what you see in this table is the whole objects factorial, and 1, 2, 3, 4, 5, 6 distinct objects. So on the one hand, it should be this. On the other hand, it should be this. But I am counting the same number in two different ways. Hopefully, I haven't done any mistakes, and this means that they have to be the same numbers. Yes? And then I am looking for my question mark. So the question mark is equal to 6 factorial divided by 2 factorials, 3 factorial. Yes, so this is the answer to this problem. So how many 6-letter words can one construct using the letters in the word pepper? This number. 6 factorial divided by 2 factorials divided by 3 factorials. So here you immediately understand what is the pattern, yes? So what you write in the numerator of that fraction is the total number of items, assuming that all the objects are distinct. But you start dividing this by each factorial when you have repeated objects. Here you see that I have I have E repeated 2 times. There is a 2 factorial coming from that in the denominator. I have P 3 times, so I have a 3 factorial corresponding to that. But if you insist, you have 1 factorial also there, which I haven't written it down, yes? In principle, we should be able to write it 2 factorial times 3 factorial times 1 factorial, but 1 factorial is the same. If you want, you can add it there, but that's okay. Is that clear? Now let me write this as a theorem. Even though this theorem is not in the book, it is discussed in problems. But if this is coming in the exam, you can use the formula, okay? You don't need to all the time convince me that this is the case, because these are standard problems in combinatorics. So this is not out of the book, it is inside the problems. But if you want, you don't need to justify it every time. You can just simply use that, okay? So let me just write the theorem here for you. So let me, I've already thought about how to write it in English. So consider n objects such that n one of them are of the first type, and 2 of them are of the second type, and for example, n sub k of them are of the kth type, such that, and so of the say I have used the word such that kth type, and this is important, if you add these numbers n1 plus n2 up to n sub k, this becomes your total number of n. So I mean that I am using all of them. I will talk a little bit about that. So consider n objects such that n sub 1 of them are of the first type and 2 of them are of the second type, and up to n sub k of them are of the kth type. And if I add these numbers, it becomes the total number of objects. Then the total the number of permutations, the number of permutations of all the objects, let me emphasize on the word, of all the objects is equal to, you have a fraction in the numerator, you have n factorial, but for each one of these types, you have a corresponding factorial multiplied in the denominator. So that's a very important formula, and I emphasize on the word all, okay? Is that understandable for everyone? So if you want to write it formally, it becomes a little bit complicated, but that's clear. So it's very important when you add the total number of types, it's equal to the total number of. So here, I couldn't ask you, I could ask you, of course, but the answer is not that simple. I can ask you how many four-letter words can one construct using the letters in the word pepper, okay? But calculating this, there is no very specific formula for that. Because if you want to write four letters, there are many possibilities for the choices you make. And after you make a choice, then there are different choices to arrange them. Keeping track of that, there is no single formula for that. Okay? I will talk a little bit about that later. So this is crucial. Here, I gave you a word with repetition, but I am asking you to write, to count the permutations if you want to use all the objects, not a portion of the objects. So this is why I emphasize on the word all. Is that clear? We will come back to this, what will happen if I want to have four-letter words. Then it becomes actually a harder problem. Any questions? No? Most of you are destroyed today, yes? So why? Okay. Let us start with another example. Uh, so just one simple example. For example, if this is given in the exam, you don't really need to justify it all the time. So example, by those conventions that I talked about. So how many 11-letter different words, how many 11-letter different words of course I don't need to emphasize on different, yes, different words can one construct using the letters in the word, using the letters in Mississippi, okay? There are some words that people who are working in combinatorics like them. So this is one of those words. So there are many repetitions when you write Mississippi, okay? Okay, so I want to wait for you to solve the problem. So it's very important. 11 letters, hopefully 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's correct. Otherwise, it would be hard. Yes, yes. Sorry, I have something in my ear. I cannot hear properly. Let me increase the voice here. Yeah, it is at the end. So what? So please, hello. Uh, no, it is very hard for me because if I want to look at the chat right now, the problem is that I have to adjust everything. You see now the camera is blurry. Yes. So if that's not very important, I will see the chat at the end. But if you are answering, it's better to just tell it to me because you see that when I come near the camera, it starts. I have adjusted with a lot of troubles. Yes. So yeah. Okay. So what's the answer? So I would write it as, so let me write it in this way. I would write Mississippi MI, and then I have SS, and then I have I, then I have two more S's, then I have two P's, then I have one more I. Yes, is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I missed something. What is that? Ah, there are four I's. Thank you. So there are four I's, four S's, and two P's and one M, and I want to use all of them. So the answer is very simple. So the answer is 11 factorial divided by what? If you want to, you can write 1 factorial for one repetition of M. It's not necessary, but I have 4 repetitions of I, so I put a 4 factorial here. I have 4 repetitions of S, I put a 4 factorial here. And I have 2 repetitions of P, I have a 2 factorial here. So that would be the final answer. And you don't need to calculate it at all. Unless you are interested to see how big that number is, you can use your calculator, for example. So this is the final answer I would expect you to write in the exam if this question is given. That's it. You don't need to calculate anything. Is that clear? Okay, let me give you another question. So example, um, so consider the word institutional. Yes, is the Trump's impeachment institutional or not? I think people are discussing a lot, yes, these days. So consider the word institutional. No, that's constitutional, sorry. Okay, and then consider the word institutional here. This is more serious problem now. How many 13 letter permutations, how many how many 13 letter, I hope that I have counted it correctly. How many 13 letter permutations? Okay, of the letters of this word it starts with a vowel. Do start with a vowel, yes? With a vowel. I think you can start thinking about the problem yourself. I will write another problem here for you. Drawing vertical lines is a little bit harder. Okay, so I'm assuming that all of these squares are the same. It's the same size. So assume, let me also describe this one and then you can think about both problems. So assume that you have an ant here and this ant can, at each step, it can go one step to the right or one step up. So for example, yeah, this ant can start from here and then another step here, one step up there. But the ant cannot go back, okay? Either the ant should go one step to the right or one step up, okay? The question is that in how many ways this ant can start here and end up here? Is the question clear? So the ant is here, the destination is here. At each step, these movements are allowed. This point with these coordinates can go to this point, x increased by 1 unit, y is constant, or xy goes to x and y plus 1. So these are the possible movements. Either we go 1 unit to the right at a step, or 1 unit up. And then assume that in how many, I want you to answer this question, in how many ways the ant can start from here and end up there. I don't know, do you have idea about this problem? Yes? Yes? No, but let us wait for that a little bit. I will come back to that. Yeah, I will come to you later. But let me just start doing this. What is your idea about? So is that right? Is it 13 letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Yes, so that's right. 13. Yeah, otherwise, it would be hard. So I want to use all of them. But let me write institutional in this way. I have one I, one N, and then one S, then one T, but I is repeated. After that, T is repeated. After that, I have a U. I have another T here. I have an I. I have an O. I have an N. And have A and L. Am I right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. So this is the word institutional. If I ask you how many permutations are there, this is easy. Yes? You just write 13 factorial divided by 3 factorials, 2 factorials, 1 factorial, 3 factorials, and after that all 1 factorials. You really don't need to write the 1 factorials. So, but this is not the problem. The problem is that I want definitely to start with a vowel. So it means that the first starting point either should be an I, vowel, or U, O, and A. These are the only options. Okay? So what is your strategy to tackle the problem? Yes? Yeah, that's also my point. I couldn't come up with another strategy to solve this problem unless you have a more clever way to do that. Yes? Do you?
One thing I thought would work but didn't work was to calculate the ratio between vowels and non-vowels.
No, that would be very hard, I think. Yeah. Yeah, might be that's also an idea. That's good, at least way of thinking, but I wouldn't dare to go for that. Yes. Yeah. But I think you are right. I was thinking also that might be I can do the same thing here. So when I want to write a 13-letter permutation, a 13-letter word, and I want to start with a vowel, then I have 1, 2, 3, and 4 choices. The bad point is that from these vowels, I have only one single one, but from I have 3 of them. So what does it mean? It means that if I start with an I, there are two still I's left that I have to use later, yes, because I want to write 13 letter words. Okay, so what can I do? So I would say that if I want to understand it better, so you don't need to do these things, by the way, in the exam. This is the way that I think. So I will consider all possible permutations, total number of the total number, yes. But then I can then divide it. It starts with an A, starts with let me start with simple ones. A. Some of them starts with O, starts with the other one A O U, and then it starts with I. Yes. If you want to use the sum rule, you have to convince yourself that these are disjoint subsets. Are they disjoint? Is it possible that there are a mixture there? No, because when you say that everything with starting with A is here, everything is starting with O is here, then definitely at least they are different at the first position, so they are totally different permutations. So there is nothing in between them. Is that understandable? Okay, so it means that I am on the safe side. If I calculate this number n1, if I calculate this number n2, n3, and n4, after that I add them together, I will get the total number of things. Okay, and then you will see that probably you didn't need to split this into 3 parts. Yes, I am making life harder for myself because A, O, and U, I have only one of them. Yes, so you agree with me that the number of items here and the number of items there and the number of items there should be the same. For example, if I start with A and when I will go and change this A with that O, then it becomes something here. So it is clear that there is a one-to-one correspondence between these. So if I calculate one of them and multiply it by 3, I will get all of them. But then I need to count the last one and add them together because I will lose the symmetry there. Yes? So let us just do it. So what can I do? Can you tell me what is N1 now? N1 means that, let me describe it for everyone if you have a little bit of doubt about this. So I have 13 positions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 positions. Let us concentrate only on this bit. I want to start with an A. Yes. So it means that I put A here and then forget about this. I need to fill up the rest. These are 12 distinct positions. How many letters are in my hand now? Again, 12. But some of them are repeated. Yes, I have already used A, so there is no A here. But I want to see how many ways I can arrange those remaining letters in these remaining positions. How many ways I can do that? It becomes, tell me, what should I write? Yes? 3 factorial because of i's. Yes. We don't need that. Yes. Finished. Yes. This is the number of elements, the number of items, permutations in this part. Yes, do you agree? But now, do you agree with me there is no difference if I start with an O? What happens then? O cannot be used again, but that the problem is the same. So N1, N2, and N3, I hope that you agree with me that all of them are the same. Agree? Yes. But now I want to go and count the number of items in the last part. Yes? Yes, you can. Now, just give me the strategy. The strategy is that I have to put an I there. Of course, I cannot say which I am choosing. There is no difference between I's. I's are assumed to be identical. So I just choose one of them and put it there. But what happens, I have to use still two i's there. Yes? And then how many options are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n4 is again 12 factorial, but divided by, I have a 2 factorial coming out from this one, and 2 factorial from here, and 3 factorials from there. So it becomes 2 factorial, 3 factorial, no, 2 factorial, 2 factorial, and 3 factorials. So the total answer is 3 times n1 plus n4, because n2, n3, and n1 are the same. So if I want to write the final answer, I multiply this number by 3 times 2 factorial times 3 factorial, and then I will add that number 12 factorial, 2 factorial, 2 factorial, and 3 factorial. So this is my final number. And that's enough for me if you write it in this way. But let us do a little bit of game with factorials. Let us see, can we simplify this as much as possible? How much we can simplify that object? This is not part of the answer to this problem. That's okay if you stop there. If you have any questions, please let me know. Do you understand what's going on? Yes? Okay. So let us simplify this. Is it possible to simplify it? Yes, to some extent, I would believe that at least we can do some simplifications. Yes. Which one? Yes, here. But this is very strange. You are right. They are the same. Yeah. So it was not easy to understand it before calculation, but after calculation, all of them are the same. No. So as you said, the ratio was probably the idea of working on ratios was working correctly, because the number of items I is 3 times larger. And this was actually, this is a double check that we calculated everything correctly. Because you are right. Instead of 3 factorial, I can write 3 times 2 factorial. Agree? And then this 3 and that 3 are cancelled. And it is left 12 factorial and 2 factorial, 2 factorial, 3 factorial, which is exactly this number. So what does it mean? It means that if I add all of these parts together, it should be equal to the items of just this single part. And I think this relative frequency was working very nice here, because we have all of them have relative frequencies. These have frequencies equal to 1, but this has frequency 3 times larger with respect to them. So I think it was more or less understandable that it should be the same. But let us see if we can simplify even more. But I don't think, yeah, we can simplify a little bit more. So what happens in the numerator? I have 12 factorials. Then I have 2 factorial, 2 factorial, 3 factorials. Am I right? This is the first one. I add it with the last one, which is exactly a copy of this. Okay, and then it means that I need to write 2 factorial, 2 factorial, and 3 factorials. I add this one to that one, it becomes 2 times 12 factorial. Yes, but 2 factorial is just simply 2. So this 2 factorial and that one is gone. So it becomes 12 factorial, 2 factorial, and 3 factorials. Usually when you simplify, it means that if you were smart enough to cook up a strategy, you might be able to come up with this answer directly. Sometimes. I don't know if you can imagine of a strategy that we can come up with this answer immediately. Might be, but you need to be probably more clever. This is much easier to understand, at least. Is that clear? How many letters are there? 13. But this is 12. Yes. Okay. Do you see why we can come directly to this answer? There should be a way, because this is a very nice number. It's not probably a coincidence No. So let us see what was institutional. Institutional. So how can we convince ourselves that with vowels? There should be a way to cook up the story for that. Yes? Is my question clear? My question is that assume that forget about this strategy. Can we come up with a very smarter strategy that we can come directly to the answer to this? And then 12 factorial is a good number. It's not coincidence because what is left for me is exactly 12. And 2 factorial and 3 factorial are exactly the repetition of these things. But why it's okay. So 2 factorial and 3 factorials are these probably, not these vowels. Okay, so what we can do, uh, uh, yeah, but there should be, this is my instinct, it should work somehow. Okay, you can think a little bit about that problem, everyone. So the problem, I will come to you, okay? If you have solved that one, now assume that the ant is going to visit his mom here and then go there. Try to find how many ways he can do that. It can do that. Okay. So one problem, the main problem that I told you here, you want the ant wants to go from here to here, no restrictions. If you solve this problem and you are okay with that, try to solve another problem that this ant has to pass through this point. This is the obligation. And then in how many ways the ant can chooses the path from that point to that point. In the meanwhile, I can think a little bit about this here. Mhm. Okay, I haven't come up with an idea, but I'm sure about it. It should be a way to find it. So, okay, so Alex, do you want to say something about this problem now? Yes, what's that? Yes?
We know that, like, for the ant to reach its destination, it has to move 5 steps upwards and 7 steps to the right in any combination
Mm-hmm.
so chooses. So we're trying to create like a instruction to it
Yes?
with combinatorics, and so it basically
But
means
1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7.
yeah.
Okay, yes.
So it's
So,
yeah.
so it means that this ant, it doesn't matter which path. Let me just solve this problem. Yes, you are right. And I will come back to you again. How do you want to answer the question? The strategy is correct. Because what he is saying is that, let us, for example, assume one of these paths, going from here to there, using the rule of the game. So, for example, this ant can come here, and then here again, and then suddenly it decides to go there, here, there, and for example, 2 steps, 3 steps, and then here. This is one possibility, yes? Yes? And then what Alex said is correct. If I just count the number of horizontal steps, it should be 1, 2, 3, 4, 5, 6, 7, but in different orders, of course, yes? So you see 1, 2, 3, 4, 5, 6, 7. So there are 6 horizontal steps, and then 1, 2, 3, 4, 5, exactly according to this number, upward steps. Yes? Okay. Uh, then what is your strategy? So let us moving to the right, call it R. Okay. Moving up, call it U. Okay. Then instead of counting these number of paths, which is harder problem to solve, I think abstractly. This is a very powerful tool in combinatorics. I told you several times. So I can give a code instead of drawing this. I can give a code to this path. The code of this path, would this trajectory is equal to R U R U, 2 R's, yes, and then 1, 2, 3 U's, yes, and then 2 R's. Do you agree? Instead of giving you the trajectory, I can give you a code. I can give this code to the ant, and the ant will follow this one and will reach from here to there. Do you agree? But this is important. I can rearrange these U's and R's. It gives you a new trajectory. Okay, but for example, let us rewrite this. For example, I have 2 R's. Let me start with 1 R. 1, 2, 3 U's. How many U's I need to use? 1, 2, 3, 4, 5. I have used 3 of them here. So let me use 2 R's here, 1 U here, 1 R here. Yes. And then how many R's I am left? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Am I right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. U's are finished. 1, 2, 3, 4, 5, 6. I need one more. Yes? So that's also another code. But let us check the trajectory for this code. What is the meaning of this trajectory? Uh, the ant goes to the right first, and then goes 3 units up. 1, 2, and 3. Yes? And then goes 2 units to the right. 1, 2. And then 1 unit up, and 2 units right, and then 1 unit up, and then 2 units right. So we got to the destination, yes? And then hopefully you agree with me, this blue trajectory is different from the red one. Even if they differ with one single step, they are different because we can recognize this. So so it means that if you give me the trajectory, I can write you a code. If you give me the code, I can draw the trajectory. So it is clear there is a one-to-one correspondence between the real problem and what counting the number of codes. But counting the number of codes is super simple, yes? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 objects, 7 of them are R's, 5 of them are U's. So as simple as that. So this is the power of smart thinking in combinatorics, yes? So this becomes 12 factorial divided by, I have 7 R's to take care and 5 U's. Is that understandable? So I have come up with another idea. Instead of thinking geometrically with shapes, I was trying to convince myself there is a one-to-one correspondence between the trajectories and these codes. And instead of counting the number of trajectories, I can count the number of codes instead. But number of codes is very simple because we just learned how to do that. Okay? Now answer this question. Assume that this ant has to pass through this point. This is an obligation. So for example, this blue curve is acceptable here. Sorry, this blue trajectory is acceptable here, but the red one is not acceptable because the red one is not passing through this point. But we want to count the number of trajectories like the blue one, which path through this. Okay? Yes?
We can use a similar strategy, but we divide it into two steps. First, it goes to that point, and then to the end point.
Okay, thank you. So, but I want to complete the problem. Okay, so you say that, okay, we can consider this problem as to a problem that can be accomplished into two steps. One steps, one step will take the ant from here to here, and now when the ant is already there, another step would be taking the ant from here to here. But each one of these problems is the similar problem, yes? I have a network here. I want to solve the problem. Okay, so can you tell me in how many ways the ant can go from here to here? So how many U's do I need? 1, 2, 3. How many R's I need? Only 2. So how many objects do I have? According to this idea of coding, I have 5 objects, yes? So it becomes 5 factorial divided by 2 of them multiplied by 3 factorial, yes? This is the number of ways that this ant can start here, end up there. Now that the ant is here, how many ways this ant can go from here to here? 1, 2, 3, 4, 5 R's and 2 U's. So it means that I have 7 factorial, 5 R's, 2 U's, yes? But now tell me, what should I do with these numbers in my hand? Add them or multiply them? I will come to you. Do you want to answer add them or multiply? Okay, just tell.
Because we use the product rule, we have like first step in the task is to select.
Just tell me add or
Multiply.
multiply. Okay, as simple as that. Yes, multiplication is correct. Why is that? Because first of all, the indication is and. I would say that the and goes from here to here and then goes to here. So this and means more or less it should be a product. And then, as you said, if you want to, I can break up this task to two stages. Stage one, this ant goes from here to here. When this is accomplished, stage two is to take the ant from here to here. But this task in total is accomplished if both steps are done. So it means that that's a product rule, okay? And hopefully, when you want to, you need to understand this number that you write as the second stage is independent of how the ant has reached to this point. We don't care. We don't care about the history, yes? We start from here. So in any ways that the ant has reached here, we can calculate. But let me make a little bit game with this problem. So in how many ways can this ant passes two specific points? Okay, so let us answer this question. What happens if the ant should pass from here, should also pass from here, and then go there? What is that? The same story. Yes, let us do it together. So now can you cook up the answer immediately? So we are supposed to pass through this point and then reach here. So the first step is exactly as before, 5 factorial, 2 factorials, 3 factorial. And then I need to go from here to here. How many ways I can do that? From here to here, I need 2 rights, 2 ups. No, 1 up. So It becomes 3 factorial divided by 2 factorial. Yes? And then I want to go from here to here. Again, 1 up, 3 r's. So it becomes 4 factorial divided by 3 factorial. Yes? And then I multiplied. So this is the answer for this problem. Let us answer another question. In how many ways this ant go there, not passing through this point? Okay, so are these calculations meaningful or not? Yes, is that understandable? I'm not writing every detail because it's recorded, so if you want, you can just go back. So now my question is that in how many ways the ant can start from here, reach to here, but avoid this point? Yes?
We take the total number of routes and then we subtract.
The one that it passes through there. Is that understandable? So that's the complement rule. Yes? So we would say that I will write 12 factorial, 7 factorial, 5 factorials minus the number of ways that I have to pass through this point. What was that? This was this problem. Yes? Am I right? Yes. So you need to write this. Yes? So that is also possible. But more interesting question, I leave it open for you. In how many ways the ant can go there, avoid this point, but go through this point? It's more interesting. Okay? So in how many ways the ant can go from here to here, avoiding this point, but the ant is supposed to pass through this point. So you need to be more clever in how to use the complement rule. Okay? I have solved one of these type of problems in the previous video that I uploaded. And that was the problem, I don't know, have you seen it or not, related to the mailbox. Okay? I was asking in how many permutations of the word mailbox, for example, A and M are next to each other, but B and X are not next to each other. So please go and watch that video. Before seeing the solution, try to solve your problem yourself. Okay? There is, I think, the last problem in the last video that I sent you the link. I'm asking you in how many permutations of the word mailbox M and A are adjacent, but B and X are not adjacent. This is, have a good understanding of how to use the complement rule, and then try to solve this problem. We want to pass through this, but no, we want to avoid this, but pass through this, or the other way around. So I want you to understand how you can solve the problem. Any questions? No? Is that understandable? Okay, so what I want to talk about later is that I told you that these formulas are good if you want to use all of them. And unfortunately, there are no very good formulas. For example, if I give you 12 letters here, and then 5 of them are U's, 7 of them are R's, if I ask you how many permutations you see, answering this is easy. But if I ask you how many permutations with length 10 you see, it's very hard. It means that you need to consider case by case. Do you understand what I mean? Because it is not very easy. But if these are distinct objects, then it is again super simple to answer that. Yes? If I give you, for example, here, how many four letter words you can make up with these letters, this is easy. We will talk about that later because there is no repetition here. When there is repetition and then you want to collect some portion of it and arrange them, unfortunately there is no particular formula for that, understandably, because there are many other, because from problem to problem the situation is different. You need to consider a lot of cases, but you can do it somehow. Okay, you need to for example, let me just give you a simple example. Can you count this? For example, I give you 3 letters 3 letters of A, let me write it in this way, 3 letters of A and 1 letter B, C. That's enough, for example. Then I ask you, for example, how many 4 permutation. This I will talk about this formally later. So 4 permutations are there, 4 permutations. By 4 permutation, I mean choose 4 objects. Okay? So if you want to count this, there is no single formula to answer this question. Yes? You need to consider case by case. 4 permutations, you need to have 4 objects. So how do you count this? How many 4 permutations are there? You need to consider, for example, one scenario is I use 3 letters A, yes, and 1 letter B. This I know how to count. 4 objects divided by 3 factorial because of repetition of 3 A's. Yes? And then, of course, I multiply it by 2 because it might be C. Yes? So this is one item. So I would say that when you say 4 permutation, one possibility is I have 3 A's involved. Yes? There are 3 A's involved. This is the number. But might be there are 2 A's involved. Yes? If there are 2 A's involved, it means that I have 2 A's, but because I want to write 4 permutations, I have to use B and C, yes, simultaneously. Then what would be the answer? The answer would be 4 factorial divided by 2 factorial because of repetition of 2 A's. And can I have an item with only one single A? No, because if there is one single A, I have only 2 letters, so that's the end of the story. I have to add them. So it doesn't mean that you cannot do it, but there is not very straightforward formula for that. You need to solve the problem case by case. Is that understandable? But if these numbers are not repeated, if these letters are not repeated, A, B, C, D, and E, if I ask you the same question, 4 permutations of this, it is super simple. We will come to a formula for that, but you even don't need the formula. Can you tell me how many of them are there? I have 5 letters. I want to have 4 permutations. You can go back to the product rule. Yes? This is exactly, I have 5 students, but I have 4 chairs. Yes? I want to choose 4 of the students and make them sit. So that's the same problem. For the first chair, I have 5 options. For the second chair, I will have 4 of them. For the next one, I will have 3. For the next one, I will have 2. So that's the answer. So, but you see that if the objects are completely distinct, it is easy to say a portion of them permutation. But unfortunately, if I have repetition, and if I am not interested in the total permutation, just a part of it, then there is no single formula for that. You have to solve the problem case by case. Yes? Is that clear? Okay. So we stop here, but still I believe that there should be a way understanding this. I will think about this. This would be a nice problem. You can also think about that. And this is not a coincidence, believe me. This is a very nice problem. So we should be able, if you are smart enough, I believe we should be able to cook up a strategy so that we can come directly to this answer without passing through these things. And so that is, in combinatorics, it's very nice if you solve problems from different perspectives, because it will teach you a lot in understanding these things. Okay, thank you very much. So now I end this, stop sharing, and now I can see the chat window. Now I see that your answer was correct, and thank you.
The recording has stopped.